Okay. So we're going to be looking at the different mutations that I want you all to know in this class. So first thing I want to point out is that this is the non-mutated normal gene that we're going to be working off of today. Every single example as we go down is going to be this sequence. We're just going to be doing different things to it to simulate the different mutations that I want you to know. So this thing is an exon. That is our gene. Okay. It's your call, whatever you want to do there. Okay. So this is what I'm having us use the different colors for. Every time that I write a non-mutated DNA sequence or messenger RNA sequence or polypeptide sequence, I will be using black. So you can use like your pencil. Every time that I am writing the mutated sequence, I will be writing it in blue. And every time that I am putting in what the actual mutation was, so like if an adenine became a guanine, I will write just that guanine, so what the actual mutation is, in purple. So that's how I'll be doing these three different colors. Okay. So what we'll do on all of these is we'll define them and then provide an example. And my hope is after today that you'll have a better understanding of what I want you to know about these mutations and how to recognize them. Okay, so first of all, a substitution is a mutation where one nucleotide is being substituted for another. So that's our definition. One nucleotide is substituted for another. What's nice about these first mutations we're going through is that they're all named very appropriately. A substitution is a substitution. A deletion is a deletion. An insertion is an insertion. They are what they sound like. So that's good. Also, I should have pointed this out before we started. These first four that we're going to go through are all occurring at the level of DNA. So these are all mutations that specifically impact your DNA. Okay. So if this is our gene, this is the original sequence. If I were to do a substitution, let's take this G right here, this guanine, and we are going to substitute it. And we are going to substitute it with an adenine. So use your mutation color. That is the actual mutation. So, if that is the only mutation, then that means that everything else in the DNA strand is going to be the same. So now I'm using my mutated DNA color. Okay. So, there is our original DNA, there's our mutated strand, and there is the actual mutation. We went from a guanine to an adenine. That's the substitution. That's not too bad. Pretty easy. Okay. These first ones are nice and fast. They get longer as we go because more steps are involved. Okay, the next DNA level mutation that we're going to go through. Will someone get the door over there for me? Sorry. A caravan of yelling people is about to occur. Thank you. I have important things to say. Deletion. A nucleotide is deleted from the DNA strand, just like it sounds. Okay. So in this one, instead of substituting this guanine, we are going to just delete it. Okay. Now what will that cause? Well, that's going to cause the nucleotides on either side to be connected together instead of this guanine. So that's going to pull in from both sides. That's cytosine and thymine that's on either side. Okay. And that will cause this. So there's where the mutation occurred. The guanine got kicked out. this cytosine and thymine are now together. And everything else is the same. Yeah, we're probably not using this recording. What's up?
I was turning in bio and it gave me a page error, so I just wanted to show you.
Okay.
So I don't know. I mean, I have it done. I don't know if I can like email
Just share it to me.
Okay.
Good.
Thanks.
All right, next up would be an insertion. This one, just like what it sounds, we're adding a nucleotide to the strand. So a nucleotide is added to the DNA strand. So in this case, let's add an adenine, because you should add adenines. I don't know. Yeah, no. And we'll do it right here in that same spot. So we're going to put in an adenine. And what that's going to do is it's going to push everything down after that adenine. Okay. So again, everything else is the same. Here is our added adenine. Okay. So what did the deletion and insertion both cause? What happened? Think about it. If you remove or add a nucleotide to a strand of DNA, what's that going to do to the rest of the strand? It's going to shift the thing. It's either going to extend it, so it's going to push it down, or it's going to retract it. It's going to shrink it in. And this can cause major issues, because if you think about it, whenever we go to make codons with the transfer RNA, that's going to make all of the codons not match up anymore. Right? So deletions and insertions are particularly bad mutations. They can have major impacts on the protein that's being made. Okay. Next up would be a repeat expansion. These get a bad rap for being really confusing, but I think it's because people don't understand why they occur. Tomorrow we'll watch a really short video at the beginning of class that shows you how a repeat expansion actually occurs. But basically, you get a small segment of DNA that just gets repeated on a chromosome. Okay. So in this one, we are going to take this ACC right here, and we're going to do it twice. Sometimes you'll hear this called a trinucleotide repeat. Huntington's disease and Fragile X syndrome are both caused specifically by trinucleotide repeats. It's a specific type of repeat expansion, but it's the one most commonly addressed. Alright, so let's go ahead and plug in the mutated strand here. So here's the mutation. We have that ACC put in there twice. Okay. Now, usually, these repeat expansions come in groups of 3. And again, we'll watch a video tomorrow that shows how this occurs. But because of that, it normally doesn't shift the reading frame one way or the other. Okay. So any questions on the DNA level mutations? Again, these are all mutations that occur specifically to the DNA. So go ahead and flip. Next up, we'll look at an RNA level mutation. So this is a mutation that is going to be impacting the central dogma at the site of transcription. So I'm going to put in parentheses here, transcription. Okay. All right, so we're going to be looking at frame shifts, and then we'll also talk about a point mutation. I didn't put point mutations on here, but we'll kind of add it. So with a frame shift mutation, it's going to be caused by an insertion or deletion. And it is going to shift the reading frame reading frame in quotes. So shifts the reading frame of the ribosome by changing the nucleotides and the codons. Remember that your ribosomes are going to be reading your messenger RNA in groups of 3 and codons. If you have an insertion or deletion by pushing the reading frame one way or the other, that's going to make all the codons after the mutation to have the wrong combination of nucleotides, which will in turn make the ribosome put the wrong amino acid into the polypeptide chain. So these can have major impacts. Frame shift mutations are typically pretty detrimental to the protein that's being made. So let's simulate this with a deletion of that same guanine. So we're going to take out this guanine here. So we're going to have a deletion. That's going to pull this whole thing in, which is going to shorten our strand. We'll see here in a second. Okay, so what does this end up causing? Well, here would be our new mutated DNA. It's going to be just like the deletion that we did on the other side. Okay, so now we need to transcribe both of these, the original and the mutation. We need to transcribe both of these strands of DNA to see what it actually caused in the messenger RNA. So let's do some transcription here. Okay, so again, the non-mutated, so the regular, the original DNA strand is in black, and we will be doing the original RNA strand in black as well. Okay, so TAC, if we are RNA polymerase, what will that code as? TAC. Oh, you're going too far. So just transcription. AUG. So this is going to be AUG. Okay. What about ACC? UGG. Okay. Again, we're going to be taking out this G, but it's there right now for original string. So GTG. CAC. Okay. Where was I? GTG. So then ACT. UG. Okay. So these would be the codons that will then be used in translation by the ribosomes. So let's see what mutated DNA, what kind of codons that's going to get us. All right, so for my mutated messenger RNA, TAC is unimpacted, so we're still going to have AUG. Okay. ACC is unimpacted, so we're still going to have UGG. But now we get to our mutation. Instead of this guanine here that provided this cytosine here, that thing's gone. So now, instead, we have TGA. What does TGA provide? ACU. Exactly. So now we have our mutation. Okay. So then we have ACU, and now we just have a lowly CT at the end. So that would go to G and A. So we don't even get a full codon at the end of the next one. Okay, so here's our mutation. And if you look, it would make sense. The guanine that got us this cytosine in the messenger RNA is gone. So now look at everything after that. So it goes ACU, well there's the ACU. And then GA, well there's our GA. So the deletion just shifted the messenger RNA down, which regrouped these codons, which is going to cause the wrong amino acid to be coded for by the ribosome. So this is an example of a frame shift mutation. They are typically quite detrimental. Okay, so what if something does not cause a frame shift? For instance, would a substitution cause a frame shift? No. It's because it's just switching two things. It's not actually pushing the reading frame one way or the other. So I didn't put this one on here, but let's go ahead and add it to the top up here. So if a mutation does not cause a frame shift, then it is considered a point mutation. Okay. You get point mutations out of substitutions. So always substitutions, and usually repeat expansions, although not always. So I would like to flip to the front real fast, and we'll add that onto the front after you finish this part. So if a mutation does not cause a frame shift, then it is considered a point mutation, and normally that's done by substitutions and repeat expansions, although not always repeat expansions. All right, so to the fronts. So substitutions, these cause point mutations. Whereas insertions and deletions cause frame shift mutations. Okay. So that's how we can get from a DNA level mutation to a RNA level mutation. Under virtual assignment, I want you to go through all three categories of classification. So you'd be telling me, for instance, that a substitution caused a point mutation, which then caused a missense mutation. So you're going to be going down the list of classifications.
Like the virtual level, we can get all of them. Do we need to go and do a different one?
Well, so every mutation on there started with either a substitution or a deletion or an insertion. So your job is to figure out which one it is. If it caused a substitution, then you automatically know that it was a point mutation. If it started with a deletion, then you automatically know that there was a frame shift involved.
Do we need one of each three though? Or?
Yes, so you'll have one of each three. And every one of them will have one of each three, because once you then get to the polypeptide level, which is the last category that we need to go through, every single mutation can either be characterized as a silent, a missense, or a nonsense. And these are our last ones. Just to make sure that we have time to get through at least the definitions so that you can use this to help you with your virtual assignment, let's go ahead and put all three definitions in first, and then we'll go back and work the actual the examples. So the definition of a silent mutation is going to be when a mutation at the DNA level does not cause a change in the amino acid sequence of the polypeptide. An easier way to say that would be it's when the mutation in the DNA doesn't impact the primary structure of the protein that's being made. So the amino acid sequence is maintained, meaning that all the R groups are still in the right spot. So you still get proper protein even if you got there the wrong way. It'd be like taking a wrong turn, but then just happening to go down a street that connects with the street you were trying to go down to begin with. You took a different path to get there, but you ended up in the same spot. So that would be a silent mutation. And we'll do an example of that here in just a second. So definition of a missense. So a missense mutation occurs when a mutation at the DNA level it's going to code for the wrong amino acids. So we'll go with results and the wrong amino acid in the polypeptide. Like maybe you were supposed to get a tryptophan and you ended up with a histidine. You're going to get the wrong amino acid in the polypeptide chain. Okay. And then the last one would be a nonsense. So in a nonsense mutation, you're going to get a premature stop codon. So when a mutation at the DNA level results in a premature stop codon. So what this does is it results in shortened polypeptides. Both missense and nonsense mutations are very likely to end up with non-functioning proteins being produced. So you're very likely to get non-functioning proteins with missense and nonsense mutations. Because with the missense mutations, you're just getting the wrong amino acid in there, so the R groups can't interact properly. With the nonsense mutation, the whole thing is just way too small. Like you're just cutting out some of the polypeptide, which is going to make it non-functional immediately. Even missing one amino acid can make a protein not function properly. Okay. So those are the definitions of the three. We have enough time to do an example for one of these. So let's just go ahead and do a silent mutation, and that way you can kind of see what it is that I'm wanting us to do. And then we'll do these last two tomorrow. We'll knock these last two out. So in a silent mutation, again, the mutation at the DNA level does not cause a change in the amino acid sequence. This can be confusing for people because it seems as though every mutation should impact the protein because of the order that things are done in. with going from transcription to translation. But here's how you could end up with a silent mutation. Let's say we did a substitution on this same guanine that we've been picking on. No, I'm sorry, on this one down here. So we're going to take this guanine right here. We're going to perform a substitution on it. Okay. And what we're going to do is we're going to take it from a guanine to an adenine. That means that everything else is going to be the same. So is this a point or a frame shift mutation? A point mutation, good. So if I wanted to classify this whole thing so far, I would say it was a substitution that caused a point mutation that's going to cause a silent mutation. You should have one from each category whenever you're classifying these things. Okay. So there is the mutated DNA. Now we need to transcribe this mutated DNA. Now we're using the exact same strand of DNA for our original non-mutated strand, so we're going to end up with that same messenger RNA sequence as before. So it's just going to be AUG and then UGG. Again, this is the non-mutated strand, CAC, so we can compare it to the mutated strand, UGA. Okay, using your codon wheel, what does AUG code for? Methionine, MET. What does UGG code for? Pull out your codon wheels. UGG, tryptophan. Where have you heard of tryptophan before? Some people say it's the protein that makes you sleepy after you eat turkey.
TRP.
That's a lie. Yeah, TRP. Or it's TRYP. So TRY is probably better. CAC, what's that?
CAC
Mm-hmm.
is
Histidine. Good. And then what about UGA? Stop. So there isn't an amino acid called stop. Okay, it's just a, that's just where it breaks off of the ribosome. Okay, so now I need to put in the mutated strand underneath that. We have just enough time to do it. So in the mutated strand, the first few codons are not impacted because our substitution isn't until down here. So TAC is still the same, so AUG is unimpacted. So we're still getting methionine. Okay. ACC is unimpacted, so we still get UGG with tryptophan. So far, this mutation's had no impact. Okay. This next one, though, I think is where we're actually going to see the mutation. So instead of CAC, we're going to get CA, what goes with A, U. So now we get CA, and then here is the actual mutation. We get a U right here. Okay. What does CAU code for? It still codes for histidine, even though we got there in a different way. So the mutation itself still got us to histidine, even though it's not what would have normally gotten us there. It still got us there. So this DNA strand had a mutation in it, but we still ended up with the same amino acid sequence. What does UGA get us to again? Yep, so we still get our stop codon at the end. Okay. Yeah, we're going to finish this tomorrow. So here we have a silent mutation. What we'll do tomorrow is we'll go through an example of missense and nonsense, but at this point, you should have enough information, along with the notes in the virtual assignment, that you could go through